Thank you very much. So thanks a lot to the real organizers of this event, first of all, for inviting me to speak here and for putting together such a wonderful workshop in this lovely city, Madrid. And thanks a lot also to the seminar organizers for making my talk also a swampland seminar talk as well. So indeed, today I'll be telling you about my pursuit of spectral bounds in supergravity, specifically in 6-dimensional n=1 supergravity. In fact, the discussion will focus mostly on the 6-dimensional F theory, but hopefully it will be made convincing enough that the ideas possibly extend also to the general supergravity setting. The talk will base on these 3 collaborations, respectively with Timo Weigand, Paul Ullman, and Kotzer Birkar. Can they see my?
No, I don't think
No.
so.
Okay. So, in fact, I was originally asked to speak about this last collaboration with Kotzer Birkar, but I've decided to discuss also the earlier works rather briefly. This way, I thought that the spirit of the program would be made clearer. So, is it supposed?
I think you have to.
Oh, yeah. Oh, and is it supposed? Oh, thank you. So, so indeed, our general motivation is to characterize the effective field theories of quantum gravity. As we know, quantum gravity theory seems to be very much constrained at high energies. But, well, and indeed, in particular, string theory is almost unique in 10 dimensions. However, at low energies, depending on the choices of the internal geometry, there arise many different string EFTs in dimensions less than 10, each of which serves as a consistent effective field theory of UV quantum gravity theory. And interestingly, at least 10 to the hundreds of allowed internal geometries are available, each leading to different string EFT. So we do have a plethora of string EFTs in lower energies. And they are part of the vast landscape of string theory, which also includes those EFTs that do not have a geometric origin. But today we will focus on the geometric part of it, which is already very vast. More generally, the entire set of EFTs is split into the landscape and the swampland, and the former contains the string landscape as the vast subset, which may or may not coincide with the full landscape. And now we aim to distinguish the landscape EFTs from the swampland ones, i.e. the good theories from the bad, by revealing general constraints of quantum gravity theory. And to this end, the string landscape can serve as a nice guiding principle if we can extract common physical properties of so many string EFTs. And in particular, we can try to establish appropriate universal geometric properties of the internal geometries in order to draw from there any common physical properties exhibited at least by all string EFTs coming from geometric compactifications. And the idea is then to recast those universal properties as general constraints of quantum gravity. So with this in mind, the EFTs in scrutiny today will be 6-dimensional supergravity EFTs with minimal supersymmetry. The field contents then organized into supermultiplets of these 4 kinds: 1 gravity, V vectors, H hypers, and T tensors. The supergravity action takes a very specific form, but we won't go through the action except noticing that the 1, T vectors, A and BIs, are some effective field theoretic parameters known as the anomaly coefficients. We'll come back to them shortly. Now, given this concrete arena of effective theories, one of the most basic questions one can ask concerns the finiteness of this arena. We may ask if the number of consistent theories is finite, and relatedly, as a necessary condition for the finiteness, our main question today will be if the discrete parameters, and in particular the spectra VHT, are bounded from above. To answer this question, most of the previous attempts in the literature relied heavily on the anomaly translation. This constrains the aforementioned anomaly coefficients A and BIs in terms of the spectrum theta. Elimination of these anomaly coefficients here may in principle lead to upper bounds on the spectra. But as it turns out, some infinite families of EFTs do survive with arbitrarily high VHT. For example, each of these families provides very large VHT EFTs, which are all anomaly-free for arbitrarily large values of K. And at this point, one could have given up on the idea of finiteness for this arena, but later on, some further constraints were considered on top of anomalies via the completeness conjecture, ruling out some of these infinite families of EFTs. The spirit of this talk, on the other hand, is to take the top-down approach instead to derive some of these spectral bounds in a systematic fashion via geometric constraints of F theory here in 6 dimensions. In particular, we will bound the U1 vector spectrum by 18 and the tensor spectrum by 567 of 10 to the hundreds of 6-dimensional F theory EFTs. The idea is then to infer from the top-down essence any bottom-up rationale by interpreting them in the pure effective theoretic language. So here is the outline of this talk. Having given some introduction, I'll start with some rudiments of 6-dimensional F theory, reminding you of how particles and strings are encoded in the compactification geometry. After which, we will address universal bounds in 2 parts. In part 1, I will analyze U1 vector sector to derive an explicit top-down bound via F theory, and then to argue for a bottom-up bound via anomalies and conjectures. Then in part 2, we will switch gears to analyze the tensor sector. Here, rather than going through the full analysis, I will instead spell out a couple of key structures involved, both from the top-down and the bottom-up perspectives. And I will also briefly discuss the bounding strategy in a nutshell. And then I will clarify the rationale behind the boundedness, manifesting the appearance of explicit bounds. And after all that, I will conclude with a quick summary. So rudiments first. At least here, we've heard a little bit about F theory from earlier talks, but let me start from scratch. So 6-dimensional F theory is a type 2B string theory on complex twofold Z2, but with 7 branes on some complex curves therein. So the axial dilaton varies internally. And here the axial dilaton profile, or equivalently the 7-brane configuration, is encoded in an elliptic vibration over Z2, of which total space Y3 is Calabi-Yau. the fibration admits a Weierstrass description of this form where f and g are polynomials of an appropriate degree in the coordinates of the base z2, and the discriminant delta is fq plus g squared, whose vanishing loci support singular fibers, indicating in turn that 7 branes are located in these codimension 1 loci in the base. In fact, the elliptic fibration encodes not only the brane locations, but also the associated multiplets. Firstly, the singular fibers in codimension 1 loci in the base Z result in the vector multiplets living on the corresponding 7 branes. The so-called minimal Kodaira fibers are classified via the vanishing orders of these polynomial triplet f, g, and delta. And the gauge algebras are immediately read off from these vanishing order data. So these algebras are the gauge algebras of the resulting vector multiplets, and they are of a semi-simple Lie type arising at finite distance in the moduli space. And the divisor classes of the loci DIs serve as the anomaly coefficients of the simple gauge group vectors. But as you can see, missing in the table are very high vanishing orders beyond 4, 6, and 12, and the corresponding singular fibers are called non-minimal. While they lack a smooth Calabi-Yau resolution, they were carefully analyzed in these works, where the fate in physics of these non-minimal singularities were identified as the affinization of the gauge algebras at infinite distance, and in turn as decompactifications of the space-time of the EFT. On the other hand, the abelian U1 vectors result instead from dissections SA to the elliptic fibration Y3. Via the M3 dual, one can see how the U1 anomaly coefficients arise as well, but the details won't matter in this talk. Let me just point out that dissections to elliptic fibration form a group, the so-called model Weyl group, which is known to be a finitely generated abelian group. So the rank of this group counts the independent sections, and in turn the U1 vectors. So the rank of this group is the U1 vector spectrum VU1. Next, the codimension 2 singular fibers at points of the base Z are responsible for the hypermultiplets. The singularities at such a point are further enhanced, and metamultiplets arise charged under the gauge algebras. And if the singularities are too much enhanced, going beyond the aforementioned minimality threshold, then the so-called conformal meta arises instead, and I'll talk about that a bit more shortly. And finally, unlike the vectors and hypermultiplets, the tensor multiplets are encoded just in the base topology, forgetting about the elliptic fibration. They arise simply from the reduction of the 4-form potential over the internal harmonic 2 forms of the internal space Z. And therefore, the tensor count T is identified with the Picard number rho of the internal space Z, modulo the trivial shift by the gravity count. And interestingly, the tensor multiplet sector intimately connects to the other sectors of the theory, as can be seen, for instance, from the conformal meta. So at a point where the conformal meta lies, one can perform a base blow up, increasing the Picard number rho, thereby generating an extra tensor multiplet. Furthermore, the used to be codimension 2 non-minimal singularity, upon blowing up, may in principle result in some remnant singularities, so to speak, leading to some vector and the ordinary matter hypers. So the tensor hyper and vector multiplet sectors are sort of intimately connected, as you can see from this tensor transition picture. Okay, so enough of the particles. Just like the 7 branes on a divisor lead to vector multiplets, an effective string arises from the 3 brane on a complex curve C. And as it turns out, the resulting string type is completely determined by the precise way the curve C is embedded in the internal space Z. Now, the viable base twofolds were classified. The full list consists of the projective plane and the Hertzsprung surfaces, along with all their blowups, amongst which, interestingly, everything but for P2 is P1 fibet. And here, the way the P1 fiber is embedded in the internal space Z as a fiber is very universal. So the effective field theories are generically equipped with a distinguished string associated to this P1 fiber in Z, which turns out to be the heterotic string. In the rest of this talk, we will focus on such generic bases with the Picard number rho bigger 1. Of course, for a complete analysis, we will have to also separately study the non-generic models on P2. This has indeed been done, but for simplicity of presentation, today we will focus on the generic analysis. So, having given some basics of wave theory, for a reminder, we are now proceeding to the universal bounds. So let's first consider the U1 vector sector of the theory. The claim is that VU1 is bounded by 18 for any EFTs of F theory as long as their tensor sector is non-trivial. So as long as the tensor count is bigger 0, we claim that number of U1s is less than or equal to 18. The derivation is rather simple. We start by noticing the nested vibration structure. So as depicted in this picture, due to the P1 fiber nature of the internal space Z2, the elliptic vibration Y3 exhibits a nested structure of elliptic / K3 vibrations. And from here, we immediately see that every section to the Y3 induces a section 2 Y2, the generic K3 fiber, via the simple restriction to the generic fiber. So from this, we see that the inclusion relation of this type holds for the model by groups of the elliptic clavia 3Y3 and the generic fiber K3Y2. And in particular, this inclusion relation implies that the free parts also they are also subject to this inclusion. And therefore, the rank of the Y3 model Y group is bounded by the rank of the Y2 counterpart. And this Y2 model Y rank, in turn, is bounded by 18. And this latter bound, 18, is simply obtained by subtracting from the K3H11, which is 20, the P1 base and the elliptic fiber of this K3. Yes.
Quick question. Is there a way, since you have at least one tensor, you also have strings, is there a way to derive this bound from anomaly input to strings or something like that?
So here I just wanted to give a very simple one-page slide summary of the geometric description, but indeed, we can use some physical argument as well in view of this anomaly inflow and so on, along the line of Kim-Shu-Baffa indeed, which I'll also briefly mention, but this also applies to geometric setup. But here I just give a very simple, a few lines of proof in pure geometry. Yeah.
Couldn't it be that certain sections are homologically inequivalent on the threefold, but after you restrict it to the fiber?
So good question. So here that doesn't happen because we may consider a generic K3 fiber. because it's a fiber, you can take the generic enough fiber so that everything is really one-to-one. Yeah. Okay. So I claim that the Y3 model by rank is bounded from above by 18 for this simple reason. And as we recalled from the Rudiment part, this Y3 model by rank is precisely the number of U1 factors in your 6-dimensional F3 EFT. So we have the same bound for V1. And this is the top-down derivation of the U1 rank bound, which should work for any geometric compactifications of F theory, at least on the generic basis, as simple as this. And now, forgetting about the geometric origin completely, we may still argue for bottom of bounds, and the claimed bounds are 22 if the tensor count is bigger than 8, and 20 if t is between 1 and 8. We have also analyzed the t equals 0 case, where a slightly bigger but still finite bound of 32 has been obtained. So let me briefly sketch the key ideas and the assumptions used here. Firstly, the anomaly coefficient A is subject to this gravitational anomaly constraint. So we may choose an appropriate basis such that the A coefficient and the inner product omega hidden in this dot take these forms. Nothing special so far. This is just a basis choice so that A and omega take this form. And next comes an assumption concerning the two-form fields and the charge strings. We assume that the strings with an integral charge in the basis just chosen here do satisfy the Dirac quantization condition. And crucially, we will rely on the completeness conjecture for the existence of all strings charged under the tensors with any integral charges, again, in this chosen basis. In fact, all we need is the presence of the string with a certain distinguished charge Q0, which takes this particular form. And we are very much motivated to consider this particular charge because this in the earlier geometric F3 setup, this corresponds precisely to the heterotic curve, the P1 fiber, which was generically found in the F3 base with self-intersection 0. So you can see from this intersection form that this has self-intersection 0. As for another assumption to be used, we assume that the strings with this charge Q0 do not generically degenerate into the instanton strings or the little strings. Then the unitarity of the resulting two-dimensional SCFT tells us that the gauge current central charge is going to be bounded from above by the total central charge, which is 20 obtained from the central charge formula. And importantly, each U1A contributes 1 to the central charge only if the level Ka is strictly positive. And the level here is obtained by as an inner product between the string charge Q0 and the anomaly coefficient BA of the U1A in scrutiny here. So the final task here is then to check if this positivity actually holds for each of these U1s or maybe some of these U1s.
Sorry,
And
what do you mean by don't generically degenerate?
So there are many such strings.
Yeah.
And by generically, if you imagine, for example, a geometric picture, I'm considering a generic fiber.
Okay.
So yeah. Okay. So then here is the final check for this positivity. Firstly, for the cases with t not bigger than 8. So the tricks are rather simple. They are very much algebraic. And physically, they just boil down to the anomaly constraints. And I haven't written this explicitly here, but we also use the fact that the inner product omega has only one positive eigenvalue. And from these two facts, we can deduce that the level Ka is always positive for any U1A factor in case T is between 1 and 8. I won't go through the details, but that's the sort of essential ingredient for proving this through some algebras. And the similar tricks also apply even if T is bigger than 8. Although in this case, the tricks have to be a little bit modified. They essentially go through and eventually lead to a slightly weaker bound, which is 22, and it's still pretty good. And here the point is that in this case, somehow it turns out that not every Ka is positive in principle. But by relaxing the bound a little bit, you can make sure that V1 is still less than or equal to 22. So this is the this is how the bottom argument goes for the abelian rank bound. And now we switch gears to the tensor sector, unless there are questions about the part 1. Okay. So so as for part 2, let me first spell out two key structures in geometry, which will play a central role in bounding the tensor spectrum T. So one is the fibration structure of Z, that Z is P1 fibered, which is generically the case, as I've emphasized enough, and which we may assume for our bounding purpose. And this was the crucial ingredient for the U1 spectrum bound in part 1, and it will be as important here. And the other key is the singularity structure of the pair Z, B, where B is a certain divisor, that the pair is 1/6 logocanonical, or 1/6 LC for short. And here the divisor of Z, the B, whose definition, well, whose precise definition I won't go through in this talk, can be essentially thought of as the discriminant locus delta of the elliptic vibration modulo this scaling by 12. And in case you are new to the notion of the logocanonical singularity, we say that the pair Z, B is epsilon logocanonical in general. Essentially, if each coefficient of the divisor B is less than or equal to 1 minus epsilon. To be precise, this definition should be made in the general birational setup, but this is sort of the working definition for this talk. Then with epsilon equals 1/6, our key principle here, the second one, tells us that the divisor B has all the coefficients less than or equal to 5/6, or equivalently 12 times B, which is roughly delta, has coefficients less than or equal to 10. And this can easily be confirmed for the minimal Kodaira fibers, as we pointed out in the paper. And interestingly, each of these two geometric structures has a very clear physical interpretation. Firstly, the integral space Z is P1 fibered if and only if the corresponding effective field theory contains a heteroly string, which is tangential at finite distance in the moduli space. And next, the pair Z, B is 1/6 LC if and only if the dimension of the spacetime is fixed to 6. And by this second statement, what I mean is the following. So we recall first that the 1/6 logocanonical structure demands that each of the coefficients of this divisor 12 times B, which is roughly the discriminant locus delta of the elliptic vibration, should be less than or equal to 10. Then from here, we gain an intuition that the criterion essentially refrains the codimension 1 fibers from becoming non-minimal. Well, we reminded ourselves from the rudiment part that the codimension 1 non-minimality triggers the space-time decompactification for the EFT. So from here, indeed, we see that this 1/6 LCNIS is essentially about the space-time dimension kept fixed to 6. And obviously, we have, of course, all the rights to impose this because we want to constrain the spectra of the EFTs in 6 dimensions, not in higher dimensions. These two key physical principles are particularly interesting as they are rather closely connected to the 2 universal asymptotic physics as claimed by the emergent string conjecture. So the precise claim of this conjecture was that at infinite distance in the moduli space, a tensionless critical string must emerge unless the spacetime decompactifies. In this talk, of course, we should consider the theories at a generic point in the modular space, not just the boundary, but the emergence of a Lie string in the boundary implies its presence even in the bulk, albeit tensionful. But that's all we need for this first structure. So in a sense, our key structures outlined here can be thought of as stemming from the characteristic asymptotic physics, which is an interesting perspective to have in mind. So for the bounding strategy in a nutshell, what we do is the following. A, we blow Z down to a Hertzsprung surface Z0, and then we go through a sequence of blow-ups phi i's, i.e. a sequence of tensor transitions, each of which generates an extra tensor multiplet. And B, we keep track of the induced divisors, PI's, along the way, zooming in onto the conformal matter. And C, we impose effectiveness and 1/6 LC-ness on the induced divisors PI's so that the 7 branes may wrap something physical and the space-time dimension may be kept fixed to 6. And the idea is that in A, if Z0, the Hertzsprung surface, is blown up as many times as the constraints in C allow, then the Picard number rho of Z is bounded by that of ZR, the endpoint of this blow-up sequence. Then, as it turns out, the number of blow-ups R cannot be arbitrarily large, and in particular, an explicit bound arises on the tensor multiplet count T. As of now, we have been able to show that the tensor count T cannot exceed 567, but this is by no means optimal, but still this serves as a nice proof of principle. So that is the upshot, and maybe in the remaining minutes, how many minutes do I have?
Or you still have 5
5 minutes.
or
Choices,
actually more towards 10.
Okay, thank you. So in the remaining 5 to 10 minutes, I'll try to give you a little bit of details to get you the idea of what's actually happening here.
So
Yes,
are you going to compare with the work of Hitchell?
I will briefly mention, but I'm not going to spend too much time on that, but I will briefly mention this result, yeah, which is very exciting. So to the details, a very useful notion to have here is that of the horizontal multiplicity. And the idea here is to make full use of the fact that all the ZIs here along the blow-up sequence, they are all P1 fibered over the common base P1b. So recall that the divisors PI's, they were keeping track of the 7 brane loci along the blow-up sequence. And we split each PI into the horizontal part and the vertical part with respect to the P1 vibration. So the former part, BIH, this part captures the internal 7 branes hitting the hetero T3 brane. And in this setting, we defined the horizontal multiplicity HI as the multiplicity of this horizontal divisor BIH at a small zi, which is the blow-up point for this ith blow-up. Then, as it turns out, HI serves as an order parameter, so to speak, of the blow-up sequence. And a very interesting observation to have here is that 12 times HI has to be an integer. And this number you can think of as the sort of local counting at the blow point of the internal 7 branes hitting the heterotic 3 brane. So just from this physics picture of this number, it is very natural that 12 times HI is integral. And from here, it follows that HI, if non-zero, is always necessarily bigger than or equal to 1/12. So they are gapped, so to speak. And we may assume without loss of generality that the blow-ups with bigger multiplicities are performed earlier, so that this sequence of HI is non-increasing. And we denote by R prime, where HI first dropped to 0 from something bigger equal 1/12. And now, having set the scene up, we are ready to address the bounds on R prime and R. Let me quickly flash through the key claims from which you can see the flavor of how the bounds arise. Firstly, for R prime, we claim that the total sum of the HIs, the horizontal multiplicities, is bounded from above. And here, rather than showing you all the details, let me just assert that this is a consequence of a global constraint coming from the fact that the internal space Z is compact. Then from this upper bound of the total multiplicity follows that R prime is bounded from above because each HI up until R prime is bigger or equal 1/12, the gap. And next, to bound R, we will claim two things. The claim number one is that if HI is 0, then the blow point Zi must lie in two vertical curves, as in this picture, as opposed to just one vertical curve. Why? Otherwise, i.e., if the blow point lied only in one vertical curve, then upon the ith blow up, the coefficient of the exceptional divisor EI plus 1 in the BI plus 1 would become negative due to the 1/6 LC-ness of the previous pair. And this is because there is no further contribution from the horizontal part of the 7 branes. And if there is only one vertical 7 brane attached to this, where this point lies, then the maximal contribution from that component is 5/6, and therefore this coefficient would be negative, which violates the effectiveness criterion. So we cannot allow for this blow-up. Claim number 2 is that for any point in ZR prime, the total number of the subsequent blow-ups there cannot exceed 11. And this upper bound is easily seen to arise from the maximal case where the two components of BR prime both saturate the coefficient bound, which is 5/6 from the 1/6 LC-ness. And if you're familiar with the conformal meta list, this is precisely the situation for the EA times EA conformal meta. Then it follows that R minus R prime is also bounded from above because there are only R prime points in ZR prime which can be further blown up, each 11 times at most. And these R prime points are the R prime points of the vertical curve intersections that you have at the level of ZR prime. So what about then the explicit bounds? Just from very simple algebras, we can address the bounds both for R prime and R. So firstly, for R prime, we get 28 times 12, which is 336. And then for R, because R minus R prime from here is bounded from above by 11 times R prime, we see that R is bounded by 12 R prime, which in turn is bounded by 12 times this bound on R prime, which is 336. So we get some 4,000. So that's some definite, concrete, explicit upper bound on R. Now, given this bound, in order to assess how good this bound is, let's take a quick look at this sort of record space, which has R equals 192. So this space can be obtained by blowing up the Hertzsprung surface F12 192 times. And you do see from the picture a bunch of EA times EA conformal meta, each of which looks like this with 11 tensors. And as I said, E8 times E8 is some maximal case for the blow-ups of HI equals 0 type. So indeed, you feel a little bit of maximal flavor, and this was indeed the record space. And people had believed that this must be really the maximal space. But now we have a better reason to think that this is indeed the maximal case. So very recently, as Miguel was pointing out, Kim, Vafa, and Su showed that the tensor spectrum T cannot exceed 193 just from the bottom-up perspective. So their argument relied on the anomaly cancellation, and they assumed a few extra assumptions, but essentially their arguments were purely bottom-up. So in any case, if you believe in this argument, then the upper bound on R should really be 192 because that's T minus 1. Whereas the bound we have derived was some 4,000. So then the immediate question is, can we do any better?
So I sort of have the converse question, which is, imagine that tomorrow somebody finds a model which agrees with your bounds, but not with theirs. What would you say went wrong in their assumption? The completeness, I would imagine the completeness of the SCFT is the...
So I haven't thought about that because I really believe that this is really going to be the true bound, but something must be wrong. Yeah, I'm not quite sure. Yeah,
Okay.
but indeed we can do a little bit better as well ourselves. So in fact, we have been able to reduce the bound of 4,000 down to some 500 or 600. Well, the general spirit of our optimization process here was to better exploit the compactness of the internal space Z, both the base and the fiber part thereof. And the at the practical level, well, we just had to group the reducible fibers appropriately, depending on how complicated they look, measured by a certain multiplicity data. And as it turns out, those fibers with a low multiplicity, relatively low multiplicity, cannot have too many components. Then it is expected that a major contribution to R should really come from those fibers with high multiplicity, so those complicated fibers. But then one can also show that there can only exist at most 2 high multiplicity fibers. And furthermore, one can also show that these high multiplicity fibers cannot have too many components either. So from these, we can try to optimize our bounding procedure, and then we have pushed it down to 566. Well, admittedly, this is not as good as 192, but the ideas are all there. I mean, this optimization process in getting to 566 was still not sort of the most optimal, in the sense that there's still much room left to for some further improvement, I would say. So, but the ideas are all there. The boundedness has been made manifest. The strategy has proven to be practical enough to give rise to some explicit bounds. And we are hoping that we can even further reduce the bound down to probably 192. And we are planning to work on this further optimization process as well. And on that positive note, let me conclude with a quick summary, if I have maybe 2 minutes.
Oh, yeah.
Yeah. So what have we done? So we have launched a program of bounding the spectra of supergravity EFTs with minimal supersymmetry. And in particular, in light of the string landscape, we have specialized at this initial stage to 6-dimensional F theory, focusing on the U1 vector sector and the tensor sector to bound their spectra. For each sector, the starting ingredient of the bound is the P1 vibration structure of the internal space Z, which leads to a heterotic string in the effective field theory. Furthermore, in bounding the tensor sector, the 1/6 LC singularity structure of the natural pair you can think of physically plays a central role, setting the decompactification threshold. And interestingly, these 2 key structures manifest a close connection between the spectral bounds and the asymptotic physics, as posited by the emergent string conjecture. And finally, given the clear physical interpretation of the geometric structures, the strategy would apply to the general supergravity setting as well, but modulo physical conjectures as illustrated briefly by this Yuan vector analysis in part 1. So that's where I wanted to stop. Thank you very much for your attention.